It looks like you're ready to start, so I think I will start too. It's 1 minute to the time. Welcome to the Fields Institute. My name is Deirdre Haskell. I'm the director of the Institute, and it's a pleasure to welcome here this workshop on Matrix-Analytic methods in stochastic models, 12th instance of this workshop. So the Fields Institute lives here on land which for thousands of years has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous peoples from across Turtle Island, and we're grateful to have the opportunity to work on this land. It's standard in Canada to make this land acknowledgement, but I'd like to add personally that I think during the tumultuous times in which we're living, it behooves all of us to remember to understand with respect and compassion the competing demands of many people who have claims on different territories. So the Fields Institute promotes fundamental research and applied research in the mathematical sciences. And we do this by bringing together people to be here in the Institute and work together to facilitate the communication and collaboration that sparks new ideas. We're funded by the province of Ontario from the Ministry of Colleges, Universities, Research Excellence and Security, by the fundamental federal government from NSERC, and by a network of principal sponsoring universities and affiliate universities from across the province and across the world. We foster an inclusive and collaborative environment in which to work, where everyone can discover mathematics and where mathematicians can make meaningful contributions to the world. And we're excited always to understand mathematics in the broadest possible sense. So we're committed to providing an atmosphere in which there's a free exchange of ideas, and we expect everybody to engage in thoughtful discussion, avoid demeaning comments, be mindful of individuals' personal space. Do remember to use the microphone so that people who are online can hear what's happening in the room. And for the people who are online, please remember to turn on your microphone and maybe even turn on your video so that we can see you and hear the questions that you're asking. We do try to make our workshops and events as accessible as possible to people who are both in the room and people who are attending from a distance. If there are any issues which make you uncomfortable, we hope that these never happen, but there are ways in which to report them, and those are available on our website. And just let me add that if you need to be connecting to Wi-Fi, there are posters all over the Institute which describe how to do it. And finally, if there's ever any emergency situation, of course, you should leave the building. And you can do so either through the doors in this direction, which go out into the patio, which towards the math department of the University of Toronto, or by going down the main stairs. And our muster point is in front of the bookstore, which is next door. And with that, let me say again, I hope you have a really great conference, and maybe I'll be able to come and listen to somebody's, at least one talk while you're here. And let me pass the microphone over to Amir to introduce the workshop.
Hello, everyone. Good morning and welcome to the 12th International Conference on Matrix-Analytics in stochastic models. Yeah, sure. Is it better? Okay. MAM 12. To be honest, I had prepared a script, of course, using ChatGPT. And this morning I was practicing reading through that my wife called and she said, "What are you doing?" I said, "I'm practicing my script." She said, "Oh, no, don't do that. You have been working for this over past 2 years, and I'll say why. And it's better to just say whatever you have is coming out of your heart. So that's why I'll try not to refer to my script. It has been a true pleasure for me to serve as one of the co-chairs, organizing co-chairs of this conference over the past 2 years, alongside Dr. Yigyang Zhao from Carleton University. And on behalf of the organizing committee, I would like to welcome all of you to the conference. We will have 25 attendees in person, participant in person at this conference, and we'll have around 32 who will join us online. And we believe that extending our audience to be from Zoom as well, it has helped to grow our community significantly, which is, I think, a good step. We started planning for this conference a little bit even more than 2 years ago, because we were hoping to host this last year, but due to some logistical difficulties, that didn't happen, and we decided to postpone it. And now, looking back, I think it was a very good decision, because it helped us to secure a better foundation for this year's conference. And I think now here I should mention that it wouldn't have happened without Phil's support. They have been very generous and supportive with this conference, and we really would like to extend our heartfelt appreciations to them for that. I also would like to mention some others who have been very supportive of this conference. First and foremost, our program co-chairs, Federico Poloni from University of Pisa and Brian Fralix from Clemson University. Thank you very much. They have been very generous with their time, knowledge, and they have been so kind and supportive. No matter how short notice was our help request, they were always there. Thank you very much. I also would like to thank the MAM steering committee. They have been with us over the past 2 years. They have been guiding us and helping us throughout the process, especially when it was kind of bumpy last year. I also would like to mention some names who have helped us in different capacities. Dr. Kim Hee, Dr. Margazota O'Reilly. I think I have to refer to my names from here. Dr. Hauran Wu, Dr. Anna Aksamit, and also hopefully soon to be a Dr. Arish Askari. They have been helping us throughout the process. I think all of these people deserve a round of applause. So thank you very much. The MAM conference started, I think, in 1995 with the influence of late Dr. Marcel Nutz. Unfortunately, I have not had a chance to meet him in person, but I know him through his work. I know that many people here have been working with him directly. I think it wouldn't be wrong if I send my heartfelt thanks to him as well for establishing this great community, which is really interdisciplinary. We have people from applied probability, business, mathematical biology, and people from across different sectors of academia. And usually we are from very different fields that we wouldn't be seeing each other at conferences. But thanks to MAM and having this great analytical toolkit, which is common among all of us, now we are together. And I think it deserves, again, another thank you to Dr. Nutz for establishing that. We will have 20 talks at the conference here, which is going to reflect our diversity and our broad spectrum of interests. And it's great. And we'll have 4 great keynote speakers. The first one is going to be Dr. Opher from the University of Toronto, and he's the CEO of SiMLQ company. Tomorrow we'll have Dr. Amy Ward. Tomorrow afternoon we'll have Dr. Mark Squintella, and on Friday morning we'll have Dr. Ivo Ada. We have planned also many other activities in between to help us with reconnecting, talking to each other, having informal conversations. We'll have our reception tonight, and then we will have our conference dinner tomorrow night, and we will have our photo session tomorrow at noon. So please make sure that you are around, because we would love to have everyone in that picture, in that family picture, I would say. And also we'll have many coffee breaks just to have our informal talks. And at the end, I would also like to remind us about the special issue that this conference will have. So please consider submitting your talks for the special issue at PEVA. That being said, I'm going to invite Dr. He to come here and introduce our first keynote speaker. Thank you very much, everyone, again, for being here and making this conference possible. I appreciate that. Thank you. Yes, please.
Morning, everyone. Well, Toronto already gave some of us a very, very warm welcome yesterday. So here again, I want to welcome you to MAM 12. Okay. Well, it is my pleasure to introduce our first keynote speaker, Dr. Opher Baron, a distinguished professor of operations management from the University of Toronto. And Dr. Baron has a PhD in operations management from the Sloan School of Management in operations management, at the Massachusetts Institute of Technology. And he has an MBA and a Bachelor of Science in Industrial Engineering and Management from the Tehran. Well, Dr. Baron's research interest, which is very wide, including queuing theory, business analytics, service operations, autonomous vehicles, and revenue management. His research offers novel approaches to various fields such as queuing theory and inventory management, and deeply explored areas such as supply chain management, and uncover new insights into all kinds of areas. His research work has been published in leading journals such as OR, MS, Amazon, Palm, and Queuing Systems, which have made a huge impact in operations research, management science, and their applications areas. Okay. Well, for me, I read Dr. Baron's paper called Omnichannel Services, the False Promise and Operational Remedies, published in 2023. And I enjoyed reading the paper and learned a lot from the use of OR and MS techniques in the management of mixed online, offline services such as coffee shop. I'm sure all of us, many of us got coffee today. And you can order online, and then now, well, traditionally you can order online. Now you can, traditionally you can go to the shop to order, but now you can order online, right? And I believe some of the system design has something to do with your work. Also, me and my colleagues, we read his paper, Supervised Machine Learning for Solving GIG1Q, which was published last year in JOC. Now, the work brings neural networks into the study of queuing models, and that inspired us and inspired me and my colleagues to further study in the direction, and you will hear from me next. Okay, and I'm sure Dr. Baron's work will have similar impact on many of our colleagues, and I think some of us are here. Okay, now due to his outstanding work, Dr. Baron has received a number of awards. For example, that 1,000 Talent Plan Scholar from the Shanghai Municipal Government, and also Radman 2023 Distinguished Scholar Contribution Awards. Dr. Baron has been invited to give plenary talks and keynote speeches at a number of conferences. Now, today's keynote is just to add one more to his long list. So, ladies and gentlemen, it's my honor to present you Dr. Opher Baron.
That was nice. I feel older than I am, I think. Maybe not older than I am, but I feel older. Having Chiming presenting me, thank you very much, man. And I want to thank everybody for inviting me here. Does the mic work? I'm not sure. Maybe yeah. I'll try it higher. Okay. If it doesn't, let me know if you don't hear me. I'll try to do more than standing here. So again, thanks again for having me. Really excited to be here. Really excited to see some of you. which by now I know for probably 20 years, and some of you which I only know a couple, and some of you I've just met today. I would like to share with you a little bit of our vision on two aspects of queuing. One of them, as Jimmy mentioned, the usage of modern tools in queuing in the context of the queuing theory part. And the other one of them is of usage of these tools in the application of queuing part. And that's where I'm going to wear my hat as the CEO of SiMLQ, which is a startup we are having now. In the middle, I'm going to bridge the gap between both of those things with a little bit of a train of thought of how to think about queuing models in the context of data. And for this, I'll have Zheng Heng here helping me, I hope, if he's willing to do that. So one of the benefits of being old is having a great group of co-authors. So this is the work we've done with all of these people, and I'll show you their pictures because that would be better. So Arik and Dimitri are co-authors on most of the papers we'll talk about today. Zheng Heng and Mark are co-authors of the main paper I'm going to talk about today. Eliran and Chezi did much of the machine learning work, and Shani has been instrumental in all of this work and some other ones that I don't have time to talk about today, but I'll be happy to chat with others after in the context of applying queuing theory with data, so how you combine them together. So this is a little bit of how I think of business analytics, and I decided to kind of upgrade my thoughts from 2021, but the main ideas are the same. We have two axes here: existing systems and alternative systems, and maybe we'll have the best system join them later on this axis. And we have past and future, kind of the time axis here. And we only have data on existing systems in the past. So if you talk about management analytics and data-driven work, all of the data is in this quadrant. And when you work with this data, the first thing you do is descriptive analytics, right? You describe the data, you analyze it, you look at it, you do all of these fun things, which is really important in the context of studying history. What happened in the past is useful, it's interesting, but one of the things you want to get out of this is to think about what will happen in the future. And this is what predictive analytics does, and this is what a lot of machine learning is very good at these days. They can really predict the future quite well in these existing systems, right? So the trick is that describing and understanding the current system is very good, but especially coming from a business school and thinking about management, what we hope to be able to do is to impact this system, right? What we take decisions that impact the system, and we're going to create an alternative system, and we don't have any data on this alternative system. And to move from the existing system to the alternative systems is a tough task because you don't have data from it. So how do you do data-driven work when you don't have any data from it? And there's a couple of Nobel Prize on this, right? 2011, 2021, kind of on moving this step. I call this comparative analytics. Basically, I want to be able to look at different systems and compare their performances. And that's a tough thing to do. It happens both in the past, counterfactuals, right? What would have happened last Friday if the doctor would show to their shift on time rather than having a flat tire? Or what would have happened if he would have a flat tire if he didn't have, right? And all of those wonderful things of counterfactuals of the past, a lot of ways statistics to do that. And in the future, which is to some extent a little bit more interesting again, is what would happen in the future if I'll price something at a specific price. Or in the question I have here, how long customer will wait in, say, my emergency department if I decided to add another nurse shift between 4 p.m. and midnight. All right, so those are things. And the trick about this is that now when I can compare different systems, I understand how will they work, what will be their performance. this is when the operations research optimization come into the game, and this is what will be prescriptive analytics, which is what we really want to do. This is the holy grail of analytics and data science and data-driven decision making, right? Let's take decisions based on data to get a better system. I aspire for the optimal one, but you know, life is life. So a better system is the first step, and that's prescriptive analytics. So if we want to go from data to better decisions making, this is, to me, a useful model of thinking of how we do that. As a queuing theorist, much of the work we are doing, much of the work of MAM for that matter, is in comparative analytics, right? I look at the system and I say I can solve this system. I do the performance evaluation of this system, and then I can also change some of the parameters and see how they impact the system. That's a lot of what queuing theory is about. Obviously, we then try to use some insight. In many cases, we use approximations, diffusion, fluid approximations to get also more easily tractable problems where we can do the prescriptive analytics and say, oh, I can optimize this asymptotic system or steady state system, and then even if my real system doesn't have rho equals 1 or infinite servers, I can take the insights and implement it in practice and get good, better systems essentially when I control them. So that's for us on that. And a lot of what I'm going to talk about today is about this comparative analytics. So any questions on this framework? Kind of makes sense? Many of you have seen it before. I just decided to make the comparative analytics bigger on both the past and future, because I think people were confused about it. And I was confused about it. So let me stop here for a second and go back to one of the things that we heard in the opening remarks from our host in Fields and from Amir as well. The world is hectic these days. If you don't recognize my accent and you don't understand that Technion is in Israel, I'm Israeli as well as Canadian, so I'm an Israeli Canadian. And Amir, my good friend here, is an Iranian Canadian or Persian Canadian. I'm not sure how you Iranian Canadian, yeah. I think, especially, I have much criticism on Canada. Don't misunderstand me. But especially in a world like today, I think the world needs more Canada. So I think I like to see thinking that brings people together, take us to a better system, not to a worse one, just because it serves my own personal interests. And if you want to chat more about this philosophical discussion afterwards, I'll be happy to do that. But let's go back to queuing. Okay, so that's what I'm going to talk about. I talked to you a little bit about how I think about management analytics. I'll talk a little bit, very quickly, about machine learning models for solving queuing problems, GG1 and GTG1, those are non-stationary essentially. And then I'm going to talk about causal queuing model. Zheng, would you like to join me when we talk about this? You've done this before so many times. You ready? Good. So I'll ask Zheng to join me there. Thank you for doing that. And then I'm going to show you a little bit of demo of SiMLQ, so you'll see how we take a simplified view of the structural causal queuing models into practice in a much more complex system. So structural causal queuing model is still a research area, almost in diapers, I would say, but not even possibly. And we've done it on really simple examples. In real life, we do it in a different approach, but the train of thought is similar. Okay, so GG1, the most fundamental queuing model, a single server, general arrival process, general service time. We know how to solve it. This is probably the main connection of this talk to this conference. This is how we solve these things. And basically, what we did, we solved many GG1s using good old Matrix-Analytic methods. And then we use a neural network to try and get basically to teach it what is the solution of the GG1. When I say solution, I'm talking about the distribution of the number of people in the system. I think we went from 0 to 50, which is fairly sensible for most GG1 systems. The trick in those things, you need to, neural networks need some discrete input. So how do I use discrete input in queuing theory? Well, I'm using moments. So we find out from our kind of numerical investigation that the first 5 moments of the inter-arrival time and in the service time are enough to get really great accurate results. The code is there for your view. You can see here examples. Those are 10 random examples where we compare the solution from the neural network to the accurate solution because we know how to solve GG1, and it does really, really well. Standard absolute error is below 0.5%. We are very accurate on the sensible percentiles, even on large deviations, kind of 99.9 percentile. The error is about 8%, which is sensible. I mean, doing a little bit of large deviation on a single SiMLQ, 8% error is not bad. Okay, so this works really well. So the idea is possibly not mathematically very intriguing. It's basically a huge lookout table, if you wish. We solve, 10,000 GG1 queues. And they say, all right, lookout here. Neural networks do it a little bit smarter than just a simple lookout that I would do. But on the other hand, what it allows us is an immediate comparative analytics for GG1Q. Because Matrix-Analytic methods take some time. And when I do my prescriptive analytics and I want to optimize things, I want to change some parameters, say my arrival rate, my service rate, whatever, takes me a lot of time to get the performance evaluation, to do the comparative analytics. Here with neural networks, once I train the model, this thing becomes really, really quick. It's not a closed form expression, but as quick as possible, I would say. So when you want to do optimization for GG1Q, this is probably the best way of getting the solutions that I'm familiar with. Okay, so this is nice, but life is not stationary. So we have an arrival process which is time dependent. Again, single server, and we want to try and understand what's going on here. Extend our process to use a long short-term memory, and the solution is there. You can see the solution, kind of how things change with time. This is I'm trying to figure out what are we showing here? I'm embarrassed. So it's the probability or let's say it's expected number of people in the queue. I'm sorry, I'm dozed off now. And basically we train for 60 periods, and you can see how we continue to be very accurate even afterwards. So that is very nice, as long as the structure remains constant. So when you have a GT process, you need to define it carefully in order to kind of see that it fits the one we have. I can think of many GT processes that would not fit what we have. But the trick is that what I need here is a little bit of memory of essentially of what's going on. I need to know where I am. And that this, if you think about fluid analysis, this is kind of another way of thinking of this queuing and analyze them. So again, you can see the results there. Good. So I finished my ML on queuing. This is additional work that has been done. This show this, similar ideas for tandem queues and so on. So it's useful, not necessarily theoretically break-taking, but very useful in terms of solving queues that we need to solve very, very quickly. Okay, so I'm a queuing theorist, as you know, and when I use data to do some comparative analytics, the way I'm thinking about it is typically, I understand the arrival process, I understand the service process, I know how many servers are there, whatever, and then I'm going to do some analysis. Will it be exact analysis or approximations or numerical analysis, all of these wonderful things. And I get them in the best case, say if I have an MG1Q, I have this closed form expression, the project finishing formula. And if you ask me, what will happen if I change my service distribution? I'll estimate the arrival rate, I'll estimate the service rate, and I can replace it with a different service rate and their variances and plug them into the project finishing formula and get the performance evaluation. The question is if Zheng Han could do the same. You want to join me? This is your time, eh? So the question is, can we use data to do comparative analytics?
Yeah, so like in this talk, I will play another role. I call this as data scientist. So what's the difference? Like compared with Opher, I only have very general knowledge of how the system looks like. I know when does customer launch. I know when does it start the service. I know when does it. However, I actually don't know the specific result of this arrival process. I don't know the arrival rates. I don't know the service rates. And even more, I don't know the dynamics of the system. I don't know how the waiting times are generated. But to that end, I also have my own advantage. I know something about causal models, which is very powerful and very general to describe different types of data generation process. And even more, I know something about statistics and machine learning, which means we have some established algorithm that tells me how to estimate such causal model from data. So now I'm looking at the same question that Opher has, but now my position is that I only have very limited domain and queuing knowledge. So to address this problem, basically in this work, we developed the so-called structural causal queuing models for data scientists to tackle this queuing problem with limited queuing expertise. And we show how to estimate such model from data, and we numerically try to test its performance. Now, like I'm in a role to compete with Opher. This is what we find. So basically, we show that in this very stylized example of single server queue, both Opher and I could achieve very similar performance. And namely, it means that if you look at this kind of simple system, it is possible to achieve as good performance as queuing theories, while I don't have much knowledge of how the queue looks like. And in the following part, we will try to go through details to see the dialogue between the two of us.
Yeah, so we used to have a fight on the stage when I said, I'm a queuing theorist for 2.5, 3 decades now. How old are you?
I'm like 25.
And this kid comes here and tries to wrestle with me on my territory, right? And we're going to look on an MM1 queue with speed up. I'll define it in a second. Not anything complicated. I know everything about this system, right? We know how to analyze it kind of very well. I put a lot of time of my life into this. And Zheng Han comes and uses different tools. We'll develop them together. We're good friends. We're not wrestling. But and competes with me. And he shows you that it's similar. This is because as the queuing theorist, I didn't feel comfortable to say that his method is better. And we have, and I'll show you, I'm not sure if we have examples here of places where he basically beats me because I don't know anything about those systems. We'll expose to you, it's in the simplest settings that we could think of. And that's what I'm going to do. I'm going to look at the event data. I'm going to define what an event log is. And I'm going to then estimate the arrival rates and the service rates. And I'm going to use the Polar check-henching formula to get the predictions of comparative analytics, right? We're talking about performance evaluations as I change the parameters of the system. Zheng Han is going to do it through his kind of more detailed approach, basically numerical method, simulation, but he's not going to simulate the queue. He's going to simulate the causal model system. All right, lots of literature on queuing theory, as you know. I don't need to talk much about it. In learning in queues and kind of working with data, we use the GG1 paper to when we want to compare it to things that we've done here. We use the ground truth from our GG1 paper.
Yeah, like in my part, our work is relevant with different strengths in causal inference literatures. First of all, we rely on this notion called Granger causality that helps us to define those informative features in the causal models.
And secondly, in queues, like customers are usually correlated. Like previous customer waits longer, then the future customer will also need to wait longer. This will be described as interference in such kind of system. And here have been lots of work in showing how to deal with such interference data. And especially we rely on this notion called G computation, which enable us to estimate the counterfactual policies from simulation in these causal models.
Good. So before we fight, let's see what we fight over. So I have an MM1 queue, and it will have speedups. So I'm going to have an arrival rate at a lambda. I'm going to have a FIFO service, and I'm going to throw a coin with probability blue P. If I get a 1, I'm going to speed you up, and I'm going to serve you at a rate mu1. If I get a 0, I'm going to serve you at a rate mu0. So mu1, mu1, mu0. You weren't lucky. Speed up didn't work for you. All right? Easy system, right? Everyone understand the system. What is the data that I want for this data? Full data. I'm not hiding anything from anyone. We're both having the same data. If you want to hide any data, you can hide it from both of us. But here we have full data. Easiest settings. The inter-arrival time, the wait time, maybe 0. After the wait time, I'm throwing this coin, right? 1, 1, 0. And given this coin, I decide on your service time, speed up or not speed up, depending on the service time. Very well-defined problem. We know how to solve it. And my question, my comparative analytics question, my performance analysis question is, what happens if I change this coin and I make it P star red? I want to save some money, speed up less, or I want to invest money, speed up more, whatever you want. What would be the changes in performance? Okay? So I'm going to look at this data from the system. I don't know that I don't know what is lambda and mu0 and mu1. I need to estimate them from the data. Right? I know that it's an MM1 with speed up. I don't know P, I don't know lambda, I don't know mu0, mu1. I estimate this from data. Okay? Good. So how do I do this? Well, I use the project hinching formula. In fact, I don't need blue P. All I need is P star now. P red, star red. And then I can use the project hinching formula because I don't know all of this. I'm going to have to estimate lambda hat, mu0, and mu1 hat. Okay? Good. That's the standard way. That's the gold standard. As accurate as you can do.
Okay.
Yes. Expected. Yes, I'm gonna. What I'm observing in the data is WI for each customer, and what we try to. My question is, what would be the expected waiting time in the system if you change its control from blue P to red star P? Thanks. Yes.
Does it matter whether the coin is tossed?
No, you can toss it at your. I mean, I can have 2 Poisson arrivals, one with speed up, one without speed up. That doesn't matter as long as it happens before I decide on the service time. For convenience, it's easier to kind of put it in this time, but it doesn't really matter.
So if you're using the full technique formula, why are you just estimating the mean of variables instead of those 3 parameters?
I can do the same. But my benefit of in the project hinching formula, it allows me to change P. I can go from P blue, which is in the system, to P red star. So that's why I want to use the formula. It allows me to do to use my tools. All right.
So, okay, like in the next part, I will introduce my approach to tackle this problem. So first of all, we will look at this components, which is called like event logs. And event logs basically show what we observe from such kind of queues. Like we denote this O bar N as the observations of N customers from the system. And for each customer I, like his observation contains like 4 parts, this PI, WI, and AI, and also this SI. So basically, we see that when we are collecting the data from the queues, we actually collect those variables sequentially. If we look at this customer I, like when the customer I arrives to the queue, first of all, we observe this PI and the difference between his arrival towards the last arrival. And when the series starts, we also observe the waiting time WI and also this action AI, which determines the following series time of SI. And when series gets finished, we observe the realizations of SI. So a natural property is, as time goes by, we are observing more and more variables that describe this trajectory of this customer I. You see that PI is a subset of PI, W, and AI, and when the series ends, you also observe this SI. So we call this as observational ordering. So, and I want to highlight that this is nothing new. This is like the common knowledge between both queuing theorists and data scientists. That's why like you see both my figure and Opher's figure show up on the screen. And the other part of the this example, I will try to go back to this single server queue to illustrate how it works. And for instance, first of all, we see these variables, A, W, T, and S. And moreover, the first component is based on the order of observed mean zone, we try to describe this causal graph that shows the connection of those variables. And furthermore, we have these assignment functions, which further tells us how to simulate those variables from this model. Let me try to give more detailed example. For instance, we follow this observational order. We start from this interval time, say this T2, and we see that, well, actually, all the customers, they will follow this Poisson levels. That's why we have their exponential densities showing up in the likelihood function. And secondly, as we are flipping this coin to decide this regular service or speed up service, we have this Bernoulli densities for the actions of AI as well. And based on this action AI, the service time SI will be different. That's why that we see this arc pointing from A1 to S1 from this figure. This is so-called this conditional densities of SI based on your action AI that customer receive. And for different customers, their levels and service times are independent. That's why we have this cumulative product capture the dynamics of n customers. And the only remaining piece in this graph is how we are going to generate the waiting time. This is the core of our performance metric. And actually we see that I just highlighted this rectangle that shows that each waiting time WI has potentially 3 causal parents. Namely, W3 can be caused by W2, S2, and also T3. The intuition is that if I am the third customer in the queue and also the second customer, if he spends like longer waiting time and service time, naturally I also need to wait longer in the queue because of first come, first serve. And we have this quantified equation called linear recursion to tell me how can I derive my own waiting time from previous customers' waiting time, service time, and also my own interval time. And if you are looking at, say, a different policy of P star, the only difference is you just replace those blue P with red P star, and you are done. So I want to highlight that this is also my own gold standard. Namely, if I'm lucky to have the true exponential densities of those service time, interval time, and also this action probability P star, I can simulate infinitely many data as I can from this model. I take the average, I can exactly estimate this expected rate as Opher who is using this Parkinson formula.
All right, so this is, we both have the same knowledge. We both know the system. It's an MM1 with speed up. I use my queuing theory approach. One can use data-driven approach. Theoretically, we know both of these approaches gives you the same end result. That makes sense? This is kind of the main thing to, everything else is built. All of our competition is built on this essence that everything, you know, both approaches are as completely accurate with the n goes to infinity. All right? Good.
Yeah. But unfortunately, like now you see in this page, only my figure is shown there, which means I don't have the help from Opher. I don't know such kind of causal model as a ground truth in my mind. That's why I try to first learn such kind of model from data. The first step is we try to define and refine this default parent site. Because in the previous figure, you see that the ground truth is previous customers' waiting time service time is calling my own waiting time. Namely, I just need to track previous one customer's data to compute my own WI. However, I am the data scientist. I don't have such kind of knowledge in my mind ahead of time. That's why I will generally assume that my waiting time is caused by previous K customers' observations, including K waiting times, K service times, and interval times, etc. And based on such kind of a general parent site, I will try to first run this algorithm by Tang et al., which help me to select those relevant features from those past K customers, and which also help me to identify the correct causal graph from the data. The second step is I just also need to estimate this likelihood. And because I don't know these interval times and service times being exponential, so I will just use their empirical density functions. And also I replace this blue P with red P star to know that I want to simulate this counterfactual policies, which is different from what I observe. The third part is to estimate this waiting time. Given the graph that we refined from the first step, we know that this WI-1, SI-1, TI, they are the causal parents for the current waiting time WI. That's why that I will solve this supervised learning problem that gives me the estimated lineage recursion, which help me to simulate the waiting time. And after I have such kind of model in my hand, so the rest of my job is just to do Monte Carlo simulation. I will simulate this interval time, action, and service time from the likelihood, plug them into this lineage recursion, which turns out to give me this sample average waiting time. This W bar will be my estimator. So I will use this right W bar to compete with Opher to see how does it perform. Yeah. So maybe let me pause here to see if you have any questions.
Does it make sense? So in the previous slide, Zhang and I had essentially the same data. We had the ground truth causal model, the ground truth likelihood ratio, and the Lindley recursion. What he explains here is if he wouldn't know this, there are tools that allow him essentially to find the ground truth causal model and a good enough estimate of the densities. It's a standard question. I mean, with nothing new about this, and then estimate the Lindley recursion, just like in Jamal's work for that matter. Yes.
I might miss something like that. P star power AI. AI is the probability.
P star is the probability of an action. AI is the AI is the action.
What does it mean for P star power AI? What is P star?
So I threw my coin. It's a 0-1. It's a 0-1 coin. So if I with probability P star, I get a 1.
Either AI is
either 0-1. Yeah, it's a binary. Sorry. Yeah. No. It's binary. Either I speed you up or I don't speed you up. Yes, Ivo.
One question.
Choose your favorite regression model. What did we use?
I think here we just use a very basic one, the multi-layer perceptrons. But in the paper, we also try like more advanced models. Like nowadays, people are using those deep generative models, like normal flow models, which turns out also to achieve very nice performance here. But actually, the choice is very general. You can try different machine learning techniques as you like. Yeah.
So we're focused here on the framework and not on its details. Each one of the building blocks here, you can choose your own favorite tool, right? So the empirical distribution, for example, right? We can use different tools to do that, right? We can to estimate the distribution based on the data. But that's not my problem, right? This is an easy solvable problem. But that's an important point of which tool you use. You need to have a good enough tool. Yes.
Would it be the case that it'd be? Could you adjust this slightly to allow P star to be a function of time? Periodic.
Yes, if you can give it to me, If you define it well for me, we can use the same process essentially, which as a queuing theory is going to be a big mess for me, right? Because there's no steady state kind of anymore that I can use, right? That's one place where this approach is easier. Obviously, as a queuing theorist, I can simulate the GG1Q, the G, right? GT1Q, but so I can do that, but I need to know the knowledge. The trick is where Zheng is better than me is when I don't have this knowledge, because he can learn it from the data directly, versus I am unaware of our community thinking of how to learn those non-standard dependencies from the data in a great fashion.
Both methods become exact as any number of samples go to infinity.
Yeah.
What's the convergence rate for the different approaches?
Good. That's the next thing. I'm going to run them.
I'm your straight.
Yeah. I'm watching the time, and I want to go forward. So this is going to be the results here. We observed 5,000 patients here, which is not a lot. Customers, excuse me. You see the queuing theorist approach in blue. The data scientist parametric when he knows just as what I know. This is an MM1 with speed up, and the data science non-parametric when Zheng just kind of we tied his hands behind his back and he has to deal with this work. We observe it with half. This is the best one to observe with. You know, if you design an A/B testing, half is probably close to optimal. And we're going to go to P star between 1% and 99%. This is the accuracy, the relative error that we have. When you speed up only with 1%, this is a high traffic system, high utilization. We all have big errors, 24% error, 22, right? So large errors. You know, I'm up kind of on the density curve. Every smallest misestimation of the utilization, lambda or mu, throws me quite a lot off. Low utilization, high speed up probability. We're very, very similar, and we are much more accurate. Obviously, we're quite accurate at 0.5, which is the system we observe. Maybe talk about the conversion, because I didn't answer you did.
Yeah.
If you remember,
So I think that the convergence of these two methods, from what I observed from the experiments, is that the queuing theorist has the advantage of like just using this formula, they will get basically get the solution just in a second. But for this data scientist methods, this is numerical, which means I still need to simulate the data from the model. That's why that is computationally like less efficient to offer. But I think that as we increase the sample size from 5,000 to 50,000, the performance between queuing theorists and data scientists are still very similar. There is no much kind of difference in terms of the sample size. And
so not completely satisfied answer, but kind of just a sense of
theoretical.
No. That's this is another example. Here's the GM1Q. So here for solving a GG1Q, again, I need kind of a more complicated machinery. Importantly, I don't have a closed form expression for the expected waiting time. So I said, oh, well, I have closed form expressions from approximations, right? I can use them. And they work kind of as expected. In heavy traffic, the heavy traffic approximations work quite well. In low traffic, they obviously don't work as well. So in this case, I don't have the closed form benefit as much. If I go, this is kind of how we use kind of the paper with the machine learning from Eliran and Chezi. But basically, this is the end result. So, yes.
For data scientists, do you need to know the high-level structure of the process? Because the conversation started by knowing that there is arrival, then there is this coin flip, and then there is service time, and then do you need to know that structure? I want to know how generalizable is this? How would it's more? It's a complex system.
Good question. We have data. In this time, we both had the same data, which included everything, including kind of what David's asked about where is the AI, where do I observe the AI, kind of a very relevant question. In principle, what I feel is a fair restriction. You say, oh, you don't really know the system, but if you want to change P blue to P red star, I need to know that this is my activity. So I need to be able to observe this action, and I need to observe the results of this action, and I need to know that this is the action I'm taking. Okay? We run this process on kind of different places where we have some control that depends on the length of the queue. So I'm only prioritizing when the queue is long enough or whatever, right? And then again, we both did it when we both know that this is the structure, that is this threshold type. But he can deal with this even if I don't tell him that. And I, as a queuing theorist, I need to know the system. So if it wouldn't be my intervention, if I'm not deciding, oh, after 5 customers, I'm starting to speed up, and I don't know that this is what happens. I just don't know that this is what happens. What I'm caring about is the arrival rate. I think that I'm intervening on the arrival rate. I'm changing prices. I'm changing the arrival rate, right? And there's also another control that I'm not aware of, which speed up the service when there are more people in the system. As a queuing theorist, no way for me to learn this kind of, if I don't know it, if you didn't tell it to. As a data scientist.
Yeah, so I think my way is, even that you don't tell me that this action AI is there Bernoulli, I can still try to identify such kind of fact from the data by learning these causal models. I think in the paper we have a very interesting example, saying that, well, indeed, the survey is more or less strategic. We know interval times are very short. We will speed up the customers. In that sense, if Opher is still like getting stuck with this Partition formula, he will make some mistake because this is no longer independent service times. But for me, I can still try to learn such dependency from data and enable me to get any accurate counterfactual estimates. Yeah.
One clarification, in the results you showed, you had 2 things, right? One was when you had to learn the causal model, and one was when you had access to it.
Yeah.
Is that correct? Like
Yeah.
Here?
Yeah.
Yeah, so I should be thinking with your question, I should be looking at the green.
Yeah, the green.
That's when I had to learn it.
The green is the yeah.
Green is where you're seeing.
Right.
Your comparison between when you know the model.
Exactly. Yes.
Yeah. Good point. Yeah.
In your formula, you had a set of functions there, because what you're really trying to learn is the function for the waiting time at time t.
Yeah.
In terms of the S, W, and T at time.
Exactly.
One. And you are therefore trying to, so sorry, that's the one.
Yeah.
You've got argmin over F in curly F. So it seems to me that curly F, the set of functions, is really important. And I don't think you told us anything about what you might put into that. So can you say something about that?
Yeah, I think that is, in this experiment, we actually use this curly F as some more machine learning models. For here, to be more specific, we consider like just a very simple multi-layer perceptron with 2 layers. This is the underlying function class that we assume.
Yeah, so it's not something you're going to write down analytically, it's what you get out of it.
Exactly, yeah.
If you want to do a regression model for this, do a regression model, right? So those,
but I would have, I mean, the question is, what's a good one of those? What's a good class of functions?
Yeah.
So I think that my take is, if you just look at lineage recursion, this is deterministic. So basically we show that even very simple machine learning models could achieve very nice performance. But as the dependencies become more complicated, like you have a much larger pattern set, or you have some random noise inherent in such kind of functions, you will need more powerful machine learning models. Yeah.
Which I'm guessing you're going to try.
11.
Yeah, definitely. I think we have lots of examples in the paper, but we don't have the time to talk it here.
Guys, I want to thank Zheng Han for his excellent work on that.
He won the best.
That's for you to mention. So yeah, we had